Hello, just a short video to tell you about pressure equilibrium constants. So we previously talked about equilibrium in terms of concentration, which is all well and good. Even if you have a gas, you can use concentration units. It's totally valid. It's not the most convenient thing to use experimentally, but it works theoretically for sure. So here's how you would describe the equilibrium constant for this reaction that we've seen before. You have the products squared because there's a stoichiometric coefficient of 2, and then you have the reactant on the denominator. All right. Now, let's extend this to talk about in terms of pressure, because that's where we want to go. So we have our nice ideal gas law. And then, well, concentration is really just moles over volume. And then you can rearrange that to say, all right, that's equal to pressure over RT. Cool. Now, we want to talk about gas law constant in terms of pressure, because that'll be a lot easier to do. So we can, in effect, play with this. So they say this is the concentration of NO2. That's N over V. That part goes right there. Then we can multiply it by RT, and then that's equal to pressure. And then schematically, I'm not going to draw a proof here or anything, but schematically, then we can say that the equilibrium constant in terms of concentration times RT is equal to an equilibrium concentration in terms of pressure. And then it's all well and good. Now, one other thing we need to do is figure out an exponent here, because for every, mole of gas in your reaction, you need to have RT once. So if you're making 2 moles of gas, well, then you have RT twice, so it's squared. If you have reactants that are 1 mole of gas, well, then you're making RT just once, or you're using RT once, and so then it's just to the first power. And if those sentences didn't make any sense, that's okay. We rephrase this as delta N, whereas delta N is final minus initial. So it's moles of product gas minus moles of reactant gas. Okay? So now we can write this, more officially, if you will, and define the pressure equilibrium constant to be just the same as the concentration equilibrium constant, except you use pressures now. And it can be its own thing, and you don't have to do all the RTs and whatnot. But if you want to relate equilibrium constant in terms of concentration to that in pressure, then you need to deal with the RT. And don't forget, the pressure equilibrium constant still has the product squared because there's a stoichiometric coefficient of 2 in there. All right, so let's expand this a little more generically. So here's A plus B goes to C plus D with the lowercase stoichiometric coefficients. So we can say the pressure equilibrium constant equals the concentration equilibrium constant times RT to the delta N, which that's what I just wrote by hand. Now I'm rephrasing it here. And, again, delta N is the moles of gas products minus moles of gaseous reactants. And so we've done this kind of logic before when we were doing thermodynamics. And so now we're doing it again here. Moles of gas products, moles of gas reactants, don't include solids, liquids, whatever. Okay, so that's it. It's pretty straightforward. You can do equilibrium constants in terms of pressure or in terms of concentration. You can relate the two with this equation, which I'll give you on your info sheet. And that should do it. One final nuance is that your textbook calls this delta nu gas because they're trying to make it different than the N that just sits by itself in the ideal gas law. I don't like this because most people look at this and say V gas. Oh, we're dealing with volumes here. And let me reiterate, this is not volumes. So again, I don't like it. This is really the Greek letter nu, which then they're using nu because it's the Greek letter for N. Basically, they're trying to swap out N with N in a different character set, but it just ultimately makes it more confusing. So if you see this in answer keys or the textbook or whatnot, just realize it's the same thing as delta N, but that I don't like phrasing it as delta V, so I don't. Delta nu, so I don't. Okay. So just a quick example problem. Here's the equilibrium concentrations at some temperature. So calculate Kc and Kp for this reaction that's listed here. All right, Kc is pretty straightforward. We've actually shown this reaction before and its equilibrium constant expression. So then you just plug numbers in. Don't forget to actually square the things. And you get an answer for Kc. Now this would technically have units of molar. But again, if you leave the molar off for equilibrium constants, I don't really tend to care. All right, so now, here it is in Kc. Let's convert it to Kp. And since we don't know pressures of everything, we should just use this form here. So Kp equals Kc times RT to the delta N, or delta nu as your book would call it. And let's plug everything in. Here's Kc, here's the ideal gas law constant, here's temperature. This has to be in Kelvin, this temperature, because you're multiplying it. So you need to have it in Kelvin. And then you get your answer. Now, here's delta N up here, right? So there's 3 product gases, 1, 2, 3. And then there's 2 reactant gases, 1, 2. So that's where that comes from. You can just pull it from the stoichiometric coefficients. And there you go. There's Kp. It's a different number than Kc, but you can still use it and do all the same equilibrium things you were doing. In your ice tables, instead of molarity, now you have pressure, and it works out just the same. It's actually rather convenient in a way. And now units on this gas law constant will be in atmospheres, which again, I don't really care about the units here, but it kind of makes sense. If you have concentration to the first power for Kc, you'll have pressure to the first power for Kp. So that works out too. And that's all we have for this video, so thanks for watching.